Hey, this is Dr. B, and welcome to week 3 here at Rasmussen College. I've got the week 3 summary here. I'll go over that, and I'll go over all the lecture material for what you need to learn in this unit. Here's the topics that we're going to learn: ions, valence state, ionic covalent hydrogen bonding, how it's related to the structure of a molecule, how we can name these molecules. We've covered that sometime last week as well. Naming ionic and covalent compounds, as well as some common acids and bases. In terms of questions, you'll see on the quiz, you'll definitely see some of these common acids and bases names, or if they give you a name, you write down its formula, both for that's acids and bases. We'll utilize information in the periodic table to come up with chemical composition. There's several questions on that. Calculate the density and the number of moles from other quantities. Mole type questions are the most common things you should learn in this unit. And here's your assignment. This is your reading and activities that you've performed. And here are the modules that have point value. And here's the point values here. It includes 1, 2, labs, an assignment, a quiz, and as usual, the live classroom. And this is a pre-recording of the live classroom. I hope you've been pacing yourself. It's now Wednesday. I hope you've been pacing yourself, taking a look at these assignments, started to do the modules, and hopefully finish up with a day to spare. This is the same general advice we always give. I do want to point out something, and that is that I was claiming that there was 15 points for including a discussion. I have to apologize for that. The 15 points is for this live classroom, both attendance and the passphrase. Please take advantage of those postings on the discussion board. However, I'll be skipping required postings on Tuesday and Sunday. There is no point value for it, but you really should take advantage of it. While I'm on the topic, the live classroom will include a passphrase, but you will not hear it on this pre-recording. I'm getting relatively low attendance for the recording itself, so you must attend the live classroom Wednesday at 7 p.m. in order to get those 15 points. So if you're looking for the passphrase on the recording, sorry, you're not going to find it there. All right, so the major topics we'll be learning for this unit are all sorts of things about the mole. We'll talk about that. Chemical bonding, as well as a very brief introduction to acids and bases. The quiz is worth 36 points, and you can expect the following types of questions, in addition to anything being fair game for all these topics. Mole type questions. How many moles are in 18 grams of water? How many atoms are in 18 grams of water? How many grams of water is 2.5 moles or 328 million molecules, that kind of thing. Mass percent is important. Empirical formula, molecular formula, shape of molecules, they'll use the term geometry. Polarity, meaning is it a relatively greasy substance that's evenly divided in terms of electron distribution, or is it polar, with one side being more rich and one side being more electron poor, leading to things that are more hydrophilic, more watery, if you will. And 3 suggestions at this point in time. I am getting a lot of late assignments. I'm seeing some students, I think, are feeling the pressure of the large number of hours that go into every week here. And is it challenging? Absolutely. And I also really want to point out that I am extremely cognizant of the fact that many of you are attempting to do the impossible. You're working 20, 30, 40, 50 or more hours per week. You're in the line of fire. You are healthcare providers, many of you. You have my utmost respect. And you have kids, some of you. You're raising kids at the same time. It's amazing. Some of you are English language learners. There's all sorts of reasons for me to be impressed by what you guys are trying to accomplish. And with that in mind, I will always be trying to save you time. I'm trying to distill the stuff down to its essence. And with that in mind, I shouldn't spend too much time on this slide. So the suggestions I will include very briefly are Try to avoid missing assignments. There's students who are just simply not handing in things. So you're going to get like a 0 out of 44. I do try to be generous with partial credit. So even if you're struggling and having trouble submitting assignment, submit it. And you have to submit it on time. I'm required to take 10% off per day. Everything's due on Sunday night at 11:59 p.m. So please try to submit it rather than not submit it. Do a little bit at a time. I'm sure you're realizing that once you check off items, it becomes more manageable. And remember why you are here. And I've alluded to that a little bit before. Okay, let's talk about that a little bit more. This unit is the mole bonding acids and bases. We're in week 3. Does it matter if you are, for example, a healthcare provider? And my apologies to those of you who may not be. That'll be the focus for this particular slide. You may be giving out medication. You may have been doing that for a number of years already. Substances in here may have different sizes of the molecules. If it's a very big molecule in a given amount of the substance, say 1 gram, it'll be fewer molecules because each molecule weighs less. So the dosage, you may require a much larger dosage for something like ibuprofen, only because the molecules might be much bigger than something like aspirin, for example. So learning about the mole can affect dosage. Having said that, the pharmacokinetics of these things and their activity is also a huge player. If it's extremely potent, then the dosage might be much lower. This applies to solids. This applies to liquids. And we'll also be talking about bonding. Every one of these molecules has ionic bonds, it has covalent bonds. Why should you care? Well, we are basically an aqueous solution wrapped up in skin, are we not? Or as they say in Star Trek, we are ugly bags of mostly water. So the bonds that are contained within our bodies will determine whether the substances are greasy and will not even dissolve in blood, whether they are hard like calcium based and are suitable for bone. And how these things can be adjusted. Your body is constantly adjusting the pH of substances and their molecular composition, and it's not a hard thing to render them from solids to aqueous liquids, and this is all part of the machinery that it's a good thing for you to understand in your field. The blood, as you know, has a very specific pH level for which is normal. Too low or too high can have unintended consequences, and it is the individual molecules, the chemical structures of these molecules that can determine this. This is a substance known as carbonic acid. It will lower the pH of blood. This is a substance known as sodium bicarbonate, also known as baking soda. This will raise the pH of blood. Knowing the bonding in these things and where the acidic part of them are and how they can actually interact with other substances is a good thing to know, a foundational thing for your career. So I hope that helps get you well inspired in terms of what you're doing and why we're not necessarily wasting your time. All right, let's take a look at a molecule of water. We'll be talking about the mole here. Here it is. It's H2O. And is this not 2 H's and 1 O? It is. You may recall from a previous lecture that the simple mnemonic, honk if you love chemistry, will tell you so much. HONC, 1, 2, 3, 4. Each hydrogen atom has 1 bond. Each oxygen atom has 2. There's 2 bonds on that oxygen atom. Here's a better look at it. So put on your nanoscale glasses, and there it is, a molecule of water. You might have expected 3 atoms that look about the same size, but they're not, and that affects everything. Small molecules have less mass, and that'll affect the molecular weight of that substance. It'll affect how many grams you need. The very small substances, a given, say, 1 gram, will have a large number of molecules, but a very large substance, in a gram there'll be fewer molecules. So oxygen is clearly much larger than hydrogen. It's 16 times larger. And if you take a look at the masses, if you do the math, believe it or not, this is about 16 times more massive than this. But we have a problem, don't we? Look at these insanely low numbers. The best balances on Earth can't do better than 6 or 7 decimal places. We have 23. These are not measurable quantities. Let's scale it up so that they are. To do that, we use the mole. And it's just a number that gives us a convenient amount of a substance. Since these numbers are insanely small, the mole is insanely high. It is 6.02 times 10 to the 23rd. Your textbook did a good job of saying it's a grouping factor. We use those all the time. Shoes come in pairs, right? That's 2. Donuts come by, oh yeah, the dozen. And paper comes by the ream. A ream is 500. You might sell things by the gross, which somehow I believe is a dozen or 144. This is a useful scaling factor if you need to get up to gram scales when a mass of 1 is only that. Can you see that's minus 23 and that's 10 to the 23? This will bring us up to useful gram scales. There is more to it, and I'll allude to that briefly. So if we have a whole mole of hydrogen atoms, now we can weigh it out. Check it out. It's 1.0 grams. By the way, hydrogen atoms have 1 proton and 0 neutrons. Notice the molecular weight of 1 here. An oxygen atom has, if you multiply it through and get a whole mole's worth, not just 1, now you got 16 grams. By the way, oxygen tends to have 8 protons and 8 neutrons. And hopefully that'll give you some clue why they picked this bizarro number. This is what you see on a periodic table. This is the average atomic mass. So when you have a mole of an element, you can just look up the number on the periodic table, and that'll give you a mole's worth. So it's a huge scaling factor. Excuse me. Okay, so if we have a mole of water, we've got 1 gram on this side, 1 gram on this side, and 16 grams on this side. That's 18 grams of water. Imagine that in a cup or as an ice cube. An ice cube might have a mass, say, of 18 grams. Very quickly, knowing that you have a mole of water, right? 6 times 10 to the 23rd molecules of water. It's a quick thing. You can say, hey, in that ice cube, there's 6 times 10 to the 23rd molecules of water. I would say that's easier than counting them one at a time. That would take you forever. And that's a nice thing to know. Now let's break it down. There are 2 hydrogen atoms. I'm seeing them for every 1 oxygen atom. That is the atomic ratio. But the mass ratio is so different. Can you see just by looking at this that most of the mass comes from oxygen? Specifically, 16 of the 18 grams come from oxygen. Water is 16/18 or 89% oxygen. The rest, or 11%, is hydrogen. That's called percent composition. It shows up a lot on the quiz and throughout the unit. So let's make sure we got it. Answer me this. I got 18 grams of water in the form of an ice cube, solid H2O. How many moles do I have? Answer, 1. How many molecules of water do I have? Well, that happens to be the molar mass, meaning the mass of a mole, and the mole is just a number, but a big number. 6 times 10 to the 23. Let's apply this to a nice silver ring. I love silver. Let's imagine it's pure silver, not silver oxide, not tarnished, pure silver, and somebody gives you a ring, perhaps because they love you, and it weighs 53.934 grams. Good for them. How many moles do we have? Notice that there's the molar mass right there, and I purposely picked a number that is exactly half of that. So we have a half a mole of silver. Does that mean we have half an atom of silver? God, no. We have half of a mole. And to take 6 times 10 to the 23rd and divide it by 2, just take that number on your calculator, enter, divide it by 2, and you just get 3 times 10 to the 23rd. This can help you save time on a test. Half a mole of anything would be 3 times 10 to the 23rd. 2 moles of anything would be 12 times 10 to the 23rd. Now, technically, you should adjust that because scientific notation is supposed to begin with a number between 1 and 10. So let's take that 12 and make it 10 times smaller. So we'll do 1.2 but we better make the exponent 10 times higher so they offset. So 2 moles would be 1.2 times 10 to the 24th. If you're entering it into your calculator, you can use the EE button if you can find it. That would be 6E23, where E equals 10 times 10 to a power. I definitely recommend you practice using a scientific calculator and do some manipulations. Try doubling it and see if you get 1.2 E24th, for example. Calculators can be kind of horrible when it comes to entering scientific notation. All right, I got a puddle of water. It's 3 grams. Now let's do some calculations that really require a little bit of look. 3 grams of water. Well, 18 grams is a mole. I have a sixth of a mole. 3 grams of water, but they don't want to know how many grams of water I have. They want to know how many grams of hydrogen I have. Now, you could, if you knew it, just take the fact that 11% of water is hydrogen. So 0.11 times this number will give you the grams of hydrogen. If you didn't know the percent composition, you could do a one-step conversion. We always start with what we're given, which is the 3 grams of water. We recognize that every 18 grams of water, which is a mole, contains 2 grams of hydrogen. Have a look. There's 18 grams of water, of which 2 came from hydrogen. So you could convert it that way. This, by the way, is 1/11th. 2 over 18, 1/9, I should say, 1/9 or 11%. And that gives you the same answer. You got 0.34 grams of hydrogen for every 3 grams of water. Let's see how many how many atoms of oxygen. This is a harder problem, right? We have a sixth of a mole. Here's how you could do it in your head. You got a sixth of a mole, so I think instead of 6 times 10 to the 23rd, it would be more like 1 times 10 to the 23rd. Let's see, and that would be how many molecules of water you have. But notice, every time you have 1 molecule of water, you have 1 atom of oxygen, so it should not change. Were I to ask how many atoms of hydrogen are in this, you'd have to double it because every molecule of water has 2 atoms of hydrogen. So we can do it mathematically. Now, if you have a way to do this in your head, feel free, but here it is if you're into the math. 3 grams of water is 3/18ths of a mole. We have a sixth of a mole. Every time we have a mole of water, it's true we have a mole of oxygen, right? Just like when we scale it down, every time we have a molecule of water, we have an atom of oxygen. And anytime we have a mole of anything, it's just a number. That should be an exponent, and that number is really big, 6.02 times 10 to the 23rd. And in fact, it matches our very quick estimate of 1 times 10 to the 23rd atoms of oxygen. Here's 2 other problems. You'll see question types on the quiz as well as just throughout the unit. These are a little harder. I got 10.82 grams of carbon, so it could be in the form of charcoal, for example, and it reacts with some hydrogen to make 12.64 grams of some organic compound that clearly has only carbon and hydrogen. What's the empirical formula of this? Empirical formula means the simplest ratio. It could be C1H2, it could be C1H4, C2H3. We don't know, but we do know that it contains 10.82 grams of carbon. The rest is hydrogen. See how they annoyingly hid the amount of hydrogen in here? We'll subtract that out from that to find out how much hydrogen is, and then we'll have a gram ratio. But that, since atoms have different masses, it's certainly not the same as an atom ratio. We will have more of the light ones and less of the heavy ones. So we'll have to turn it into moles, which is number of actual particles, in this case atoms. And then we'll turn that mole ratio into a nice clean number. So we start with what we're given, the 10.82 grams of carbon. We recognize that 12 grams, if you look it up on the periodic table, you'll see 12.011 there. 12 grams is a mole, so we have close to a mole of carbon. And we have 1.82 grams of hydrogen, which is actually more than a mole. A gram of hydrogen is about a mole, so we have 1.802 moles of hydrogen. This is a true representation of the relative number of atoms. And can you see that it is 2 to 1? Maybe you do, maybe you don't. The trick to turn this into whole numbers, and I want you to put this in your memory banks, is quote unquote, divide by the little guy. The little guy is 0.901. If I divide both sides by 0.901, well, I guarantee you the little one is going to turn into 1 because it's dividing by itself. So we have 1 to 2. C1H2, or that is for every carbon we have 2 hydrogens. They oftentimes go on at this point to say if that's the lowest ratio, what's the actual ratio? Is it C1, C2H4? Is it C3H6? Whatever, right? Well, they have to tell you how many, the molecular weight of the substance. And it's not 14, is it? 12 plus 2 does equal 14 grams per mole, but this is triple that, 14, 28, 42. So the answer is going to be C3H6. To do that, just scale it up. Just keep adding 14 until you get to 42. And if we have 42 divided by 14, that is 3. So the molecular formula is C3H6. This might have a molecular structure like this. Very small molecule. Okay, that's enough to answer, I don't know, about half the questions in this unit, and it's all stuffed into there. Let's go on to talk about bonding. Now, I'll talk about bonding in a few slides. There are not many questions on it in the quiz, so if you're in a real hurry and you're focusing on the quiz, you can go over this a little more briefly. However, if you really want to learn this topic, and I think you should, and you have the time, and I hope you do, take the time to follow this. Okay, here we go. What's a chemical bond? Well, it's that line right there, but there's no real lines between the atoms. There's some sort of attractive force. I'm not going to use the term bond to describe bonds, so we'll call it a force that holds 2 atoms or some other particles that could be ions together. Ions being charged atoms. It's really useful to notice that this last column here does not form any chemical bonds. Those are the noble gases. The reason atoms do form bonds is because they need that noble gas configuration for stability. These have the 8 valence electrons, all the other ones don't. If they have 7, they'll gain 1. If they have sodium, they'll, like group 1, they'll lose 1, and you'll get a nice bonding pattern. There's 3 major types. If it's just between metals, now here's a little periodic table here. Let's focus on the staircase right there. Very few of the atoms on the periodic table, that is the elements, are nonmetals. They're mostly metals, like nickel and platinum and things like that. Anything to the left of the staircase is a metal. So if you just have metals bonding together, not surprisingly, we'll call that a metallic bond, like a chunk of iron. Iron, for example, is one of those substances that humans would die without. We need it in trace amounts. By the way, 95% of the human body is hydrogen, oxygen, nitrogen, and carbon. Okay, if you have a metal and a non-metal, well, these will lose electrons, these will gain. Positive is attracted to negative, so you'll form what's known as an ionic bond. Think of them just as salts. And as you know, the human body uses salts in a very exquisitely beautiful manner. Every substance that can enter or get out of a cell is adjusted by salts. An example of that would be sodium chloride. Sodium being over here, chlorine being over there. Finally, we're made mostly out of substances that are over here, and it's mostly those 4 elements that comprise humans: hydrogen, oxygen, nitrogen, and carbon. Hydrogen is an exception, it's right there, but clearly hydrogen is not a metal. So these are known as covalent substances, and carbon-chlorine bond would be an example. There are something called covalent network solids. I'm going to skip them. Things like diamond. Okay. Now, just because something is sharing electrons, which is what these things do, they share the electrons. Each line represents 2 electrons. And if they do so evenly, they are greasier. We call that a nonpolar covalent bond. This stuff would not dissolve in the bloodstream, for example. If it is a carbon to oxygen bond, the closer you are to fluorine, the more you will hog the electrons. We call that electronegativity. Oxygen's right next door. It's going to be pulling electrons away from carbon, which is more to the left. And so you'll have a little bit negative here, since electrons have a negative charge, a little bit positive here. Slightly salty, if you will. That's called a polar covalent. bond. Methanol will dissolve in water. Methanol will dissolve in your bloodstream. Ethanol, which is booze, will dissolve in your bloodstream. And boy, oh boy, does it have an effect. Here's a substance that has a carbon-hydrogen bond. Now, although they're different elements, they have very similar polarities, and hydrocarbons are considered nonpolar. Excuse me. Okay, so I got a bunch of bonds here. Tell me if it is ionic, covalent, or metallic. If you have a periodic table out, and you'll need it for the rest of this lesson, I recommend you get it out. And just look for whether things are both to the right, both to the left, or one of each. You should recognize that sodium chloride is an ionic compound because it has a metal to a nonmetal. Fluorine to fluorine, they're both right of the staircase, so covalent. In fact, they're identical, so let's go one step further and call them nonpolar covalent. Phosphorus to oxygen, take a look, convince yourself they're both to the right of the staircase, but different. Oxygen is a little more electronegative, therefore polar covalent. Magnesium to chloride is ionic because magnesium is a group 2 metal, chlorine is a group 7 nonmetal, so that's a salt. This is all to the right of the staircase. You might recognize this is carbon dioxide, therefore it is a polar covalent bond. We'll have more to say about that because this is not necessarily a polar molecule. And the sodium to oxygen bond is clearly metal to nonmetal, so we'll call that ionic. Metal to metal, metallic, nonmetal to nonmetal, covalent. This happens to be an example of something which we're going to skip, which is a covalent network solid. Okay, another topic. Now, this is something you won't see a lot of questions on the quiz, but it's an important thing, and this is really to gain a deeper understanding of chemistry. And this has to do with ions and their types. Say you got a salt. It's in the bloodstream. Say it's sodium chloride, for example. That's fine, but some of them are not. Like, for example, if I have sodium carbonate, right? The carbonate is not a single atom, it is multiple atoms. Multiple as in poly. So polyatomic means you can have ions that consist of more than one ion. Here's a climber climbing limestone, limestone being calcium carbonate. And the charges, if you look them up, the calcium's right there, it's +2. A carbonate is not an element, it is a group of elements that combine to form a -2 ion. We call that a polyatomic ion. So chalk is calcium carbonate, and there you go. Carbonates are distributed in the bloodstream. They are a big part of the blood adjusting pH. They are very significant for the health fields. Let's do another one. The carbonate was the polyatomic ion. Sodium cyanide, yikes, 60 milligrams is a lethal dose. That's just a tiny pinch. That's definitely biorelevant. That's NaCN. Notice Na is plus, but the entire Cn minus is your minus part. Calcium hydroxide. That's also known as quicklime. Calcium is 2 plus. The hydroxide, if you looked it up on a common table, you would see one on most periodic tables. It's -1, so we need a +2 and a -1. We need 2 of these -1s to offset the +2. Therefore, the group 2 hydroxides require 2 of them. +2 and 2 -1s makes -2. Now, also, if you have an ion, it might be just monovalent, meaning it's +1, +2, +3, but there's an entire group in the center here, and we talked about this last week, that are polyvalent. They have multiple charges. What a pain. The way we deal with that is we include the charge when we name them. For example, if you were in the hospital and you, for some reason, needed some titanium chloride, you better ask which type, because titanium 4 chloride has a +4 charge on the titanium. But titanium can also be +2, and we name that one titanium 2 chloride. So watch out for these central ions. They have multiple charges. Iron 2 cyanide must be Fe. Write a little +2 above it. Find the charge on a cyanide. It's -1. Write a little -1 above that as a personal note. Drop and switch, and that's the formula for iron 2 cyanide. Don't take this too far because only the central atom is polyvalent. To name something like sodium chloride, don't say sodium 1 chloride. Sodium is always +1, so we simply say sodium chloride. You may have noticed this topic is known as polyvalent and polyatomic ions. This is a deeper look at ionic compounds. I also want to take a few minutes of your time to take a deep look at covalent bonding. Once again, this is something that does not show up in terms of a lot of questions, but it's very important and I want to spend a few minutes on it. It's a bond based on sharing electrons. Most of the elements in our body are doing that, so it's a good thing to understand. If you take a look at this little image here, you might notice that there's 7 valence electrons here, and you might recall that they want 8. So this could be, for example, 2 chlorine atoms coming together. And if you can see this quickly enough, you might be able to say, oh my God, I get it. If these things share 2 electrons, blammo, they will each have 8, right? There, 8. And I'm 8 on the right, 8 on the left, if they can share those 2 as a covalent bond. I hope you understood that. Okay, so atoms want to fill their outer shells. It's their reason for being. We can approximate this very quickly with electron dot structures. So just find the number of valence electrons, that's outermost shell electrons, great predictor of their reactivity, and draw them. Since it tends to max out at 8, just draw 2 per sides around a square and try to spread them out, and it will predict bonding behavior. Hydrogen has 1 valence electron, it tends to form 1 bond. Oxygen has 6, so draw 2 per side, but try to spread them out. 2, 4, 5, 6. I think that's a good job. Oxygen tends to form 2 bonds. Nitrogen tends to form 3. Remember, honk if you love chemistry. 1, 2, 3, 4 bonds. So when you draw off the 5 valence electrons that nitrogen has, you end up spreading 3 of them out because you can, 2 per side, and that correctly predicts that nitrogen will have 1 lone pair of electrons. That's what they call these. They do not participate in bonding, but it tends to form 3 bonds. Those 3 guys will want to pair up. Carbon forms 4 bonds because it has 4 valence electrons. I'm now going to show you a quick animation of the whole idea of a covalent bond. Check this out. Oh, by the way, hydrogen, oxygen, nitrogen, carbon, 1, 2, 3, and 4 bonds. Lone pairs are things like this that you see. I don't see them on hydrogen. I see 2 on oxygen, 1 on nitrogen, none on carbon. And here's the animation I want you to focus on. When 2 fluorine atoms come together, if they choose to share those 2 central electrons right there, and they will, they now both have a full octet, as they say. 2, 4, 6, 8, 2, 4, 6, 8. This is the entire reason why covalent substances will share an electron, is to obtain that full outer shell of electrons. Lewis structures. Now here there's several questions on the quiz, and I want to make sure you get it. Here's that animation again. 2 fluorine atoms combined together. And in fact, you can take any of the common atoms and draw their dot structures, right? 1 valence electrons, draw 1 dot. Oh, 4 valence electrons, draw 4. 7 valence electrons, draw 7. And 8 valence electrons, draw 8. And this is a fantastic predictor of bonding behavior, right? These will tend to form 1 bond, 2 bonds, 3 bonds, 4 bonds. Since 1 pairs up here, they don't form 5 bonds, they tend to form 3. Huge caveat. First row, that's 1 shell, you're fine. 2 shells, you're fine. Once you get to the 3rd shell and beyond, there can be exceptions because of, well, I won't go into the reasons why, but as things get bigger, you can get weird things. They can form unusual numbers of bonds. Okay, so here's the Lewis structure of water. There's each of their dot structures, and when they come together covalently, can you see I just throw that one over here and that one over here? Do these not all have a full octet? Oxygen, yeah, 8. Maybe I even draw it. There you go. Hydrogen is in the first row, so it only needs 2 because helium has 2 and it's stable. There it is. There it is. It's good. And you can draw, anytime you have 2 dots between atoms, you draw them as a line. That line is assumed to mean 2 dots. Don't forget you can form double bonds. Here's carbon dioxide. Is it stable? Yeah. Carbon has 8, each oxygen has its 8 electrons, 2, 4, 6, 8. 8 electrons on that one by sharing 4. Carbon shares 4 as well, and those are your 2 double bonds. Try drawing N2 and it'll look weird. Look at that. What I did was I started with N1, 2, 3, but recognizing that nitrogen tends to form 3 bonds, you could just draw those 3 lines right, recognizing that those 2 bonds represent a pair of electrons. I see 3 of them there, so we could simply draw this as nitrogen N2 with the triple bond there. It helps a lot to recognize that nitrogen tends to form 3 bonds and have 1 lone pair. And you should see that N2 is stable, 8 electrons when it shares those 6, 8 electrons when it shares those 6. That is the essence of covalent bonding. All right, now let's talk about the ramifications of that, how that can affect the shape of molecules. This is known as valence shell electron pair repulsion theory, but just think of it as shape. And this does show up frequently in terms of assigned problems as well as things on the quiz. If you're going to try to figure out what the shape of a molecule is, it's important. Certainly in the medicinal field, that topology or that shape determines its activity. Combine that with where the electrons are, electron poor regions, electron-rich regions, and it's like a lock and key. It will go to a receptor site and it can cure a disease, for example. Let's first take advantage of the things we already know from dot structures. Halogens, that's symbol X, fluorine, chlorine, bromine, and iodine. Convince yourself they're group 7. Convince yourself they have 7 valence electrons. They will have 3 lone pairs and 1 bonding electron. Similarly, we can apply those same rules, and you'll see these kind of things for halogens, like bromine. Hydrogen, no lone pairs, 1 bond. Oxygen, 2 lone pairs, 2 bonds. Nitrogen, 1 lone pair and 3 bonds. Carbon, with its 4 valence electrons, will form 4 bonds. These are tinker toys. These are how they come together. And this can be combined to form molecules like carbon dioxide. Notice carbon has its 4 bonds. Notice that oxygen has its 2 bonds and 2 lone pairs. They can twist around like that to form multiple bonds, so be aware. So that's the first thing to do when you see a substance. If it's just honk molecules and maybe a halogen, stick them together by using what you already know, and you get a fast answer to what the molecule, how it will be assembled. Another quick hint is always put the largest number of bonds in the center. So nitrogen, carbon will clearly go in the center. Everything else will satellite around it. If it doesn't fit for these rules, you have to add up the total valence electrons, spread them around the central atom, and then any extra electrons would go to the center. There's carbon tetrachloride. We can solve that using simple honk rules. There's phosgene, carbonyl dichloride, COCl2. That belongs to this HX honk rules, and we can just stick them all together. Now, when that happens, they will assume a shape. Notice that this has 1 central thing and 2 things around it. This has 1 central thing and 4 things around it. This has a central atom and 3 things around it. Recognizing that they're full of electrons which are repulsed by each other, they will try to spread out, and as a result, a shape will ensue. So if you have 1 central thing and 2 things around it, it's pretty obvious that the furthest away they can get from each other is linear. So CO2 will be a linear molecule. If there are a pair of non-bonding electrons on the central atom, like nitrogen, like maybe oxygen, they take up space. They don't bond anything, but they take up space and they perturb the shape. So if you have, even if this had lone pairs on it, there it is, number of lone pairs, none. Shape is linear. This kind of gets repeated here. Now suppose you have an AB3 system, a central atom, 3 things around it. Can you see how this will assemble itself in a triangle with 120-degree bond angles? See how they're bigger than 90 degrees? We call this a trigonal planar structure, and it looks like that. Central atom, 3 things around it. Now imagine that one of them is not a bonding electron, but rather a lone pair of electrons. Well, you'll get space here, but nothing attached to it. This will result in a bent sort of shape. So if you have that sort of situation, that's its shape. Now imagine you can have four things around a central atom. You might think that they can assemble themselves in just sort of 90-degree bond angles, but you're only thinking in two dimensions. If you can involve the third dimension, right, go three-dimensional, you can hopefully see how these can assemble themselves in a tetrahedral shape. And that may show it to you there. It's clearly better than the 90 degrees you'd predict if it's just flat. So AB4 systems like this one, right, like a lot of things, will have a tetrahedral shape with 109-degree bond angles. If one of them is a lone pair, for example, ammonia, NH3, that dot will put up, just think of that as a space occupier. Now look at that shape. You might recognize that as a pyramid, a three-sided pyramid, so we call that a trigonal pyramid. It's very common to have a central atom that has two lone pairs, mainly oxygen. They both occupy space and those two things around it. So just replace that one of these with electrons, and you end up with a bent shape with 107 degrees or so for your bond angle. That's a super important shape because that's what water is. HOH, those two bonds will be now lone pairs. Shape of water is bent. Let's apply it to these four substances. If you can figure out the shape of these and draw them, you are an expert in shape. Now CH2O will do the fast way. We know that carbon looks like that, hydrogen like that, and oxygen like this, and we'll just assemble it, drawing carbon in the center since it forms the four bonds. And you should get this. First you would draw C to H to H to O, and you'd say, ugh, I got my two lone pairs on oxygen, but it doesn't have two bonds. I've got my carbon, but it only has three bonds. Don't forget they can multiply bond. This is perfect. Oxygen, two lone pairs, two bonds. Carbon, four bonds. Hydrogen, one bond. This is an AB3 system. Get it? One thing with three things attached. Its shape will be trigonal planar. Here is ammonia. Let me just do it piece by piece. NH3. Draw that in the center because it has three bonds. Attach hydrogens to each one of those because it's a nice link up with there. And there's the shape there. Now don't consider that to be trigonal planar. It's an AB4 system, not an AB3, AB4. 1, 2, 3, 4. It would have been tetrahedral, but one of them is a lone pair, so there it is right there, trigonal planar. Try it for CH4. Draw your carbon. Hey, that honk rolls. We should be able to do that fast, right? So draw your carbon with its four lines. Attach your four hydrogens. And what would be the shape? That's right, tetrahedral. Last one is going to be a phosphate here, and I'll show you what the shape of that one is. Now, this one is the most challenging one, so I'll do it briefly. If you struggle with this one, it's okay because it's the most complex. We've got one phosphorus, four oxygens, and three extra electrons. Let's add up the total. That's 5. Notice phosphorus is group 5. Plus 4 times 6, each oxygen is group 6. That gives us 29. 3 extras makes 32. So I would draw phosphorus in the center, all 4 oxygens around it with a single bond. Now that would mean phosphorus would only have 4 electrons that it's sharing, and that's no good. It would have the 32, and each oxygen would have a negative charge. To adjust that so it's more reasonable, we're going to make this oxygen a nice normal garden variety oxygen with 2 lone pairs and 2 electrons. Every other one, convince yourself it has a negative charge. 2, 4, 6, 7, 2, 4, 6, 7. This is PO4. It is 3 minus, and that's the shape of the phosphate trianion. It's an AB4 system, so we would predict it to be tetrahedral. One quick thing I want to add to it, because it does show up, is that it's observed that the bond lengths for this substance are all the same. How can that be? Single bonds, as you might imagine, are the longest. Double bonds get shorter and triple bonds shorter still. And yet all of these bonds are the same. This is not an accurate representation of this molecule. This has double bond character, but it's spread out between that one, and that one. We call those resonance structures, and the phosphate anion consists of 4 bonds that are all the same bond length. Final topic. A little bit about solvents, acids, and bases. Now, rarely do chemicals react in the solid phase. Imagine a chunk of one rock reacting with another rock. There's not good surface area interaction. They can only react on the surface. So scientists learned a long time ago that it's best to dissolve substances. That means you add a solvent. They help for three reasons. One, now that the ions separate in solution, sodium chloride, you throw it in water, it separates into ions. They're all spread out. They're not a big chunk. You'll get over 1,000 times increase in reaction rate. They'll absorb heat, so things won't change temperature as much, and they will also transfer easily. All three of these are the reasons why humans also contain a solvent known as water. One, all the molecules in your bloodstream and throughout your body, if they're dissolved, are separated into individual molecules. They will react so much faster. Two, we are warm-blooded creatures, and we use water, which has an insanely high specific heat. Very hard to change the temperature of water, so it's a great solvent system for a human or any sort of life form which has to exist in a specific temperature range. And three, solutions transfer easily. We eat and drink things that are solvent-based. I guess drink mostly, right? But if you have things that are dissolved, they can get into the bloodstream quickly. So our foods are transferred into our body so often in the form of aqueous solutions. And some of the substances that we eat and some of the substances in our body are classified as acids and bases. I'll very briefly say what an acid is. Consider water, HOH. It's a little bit H plus and a little bit OH minus. An acid is anything that has H plus or raises the pH, lowers the pH of a solution. A base is something that has OH minus or raises the pH of a solution. Common acids include hydrochloric, acetic, sulfuric, nitric. Common bases is anything that ends in hydroxide, like lithium hydroxide, sodium hydroxide, magnesium hydroxide, aluminum hydroxide. And notice these tend to all begin with H. And in fact, acetic acid you'll oftentimes see written as HC2H3O2. That H is the H plus that all acids must contain. You should know these structures and you should be able to give them names. So if I said HCl, you'd say hydrochloric acid. If I said HI, you'd say hydriodic acid. HBr, hydrobromic, etc. Bases have to end in OH, and if it's a group 1 metal in front, it forms +1. That will nicely offset the OH minus, so you only need one of each, like here and here. However, if it's a group 2 metal, and magnesium is, it'll form a +2 charge, and you need 2 hydroxides to offset it. Aluminum hydroxide, aluminum is +3, so aluminum hydroxide is AlOH3. Okay, that is the entire topic of for week 3. I hope that helped. Send me emails if you have any questions at all.